All right, we are back. Last time we looked at the definitions of nullable, first pause, and last pause, and here they are. And we will start off by trying to apply these definitions to the tree we have here. Okay, I'm using my iPad with the same tree, which corresponds to the regular expression we are dealing with, and that is a plus b star ABB, right? So that's the expression. Oh, can't see it. Maybe I should write it up here. A plus B star. Let me write it on the left side here. A plus B star ABB and a hash. So we're dealing with that regular expression, okay? So the definitions are nullable, first pause, and last pause. And if you look at the interdependency, nullable is defined on its own, okay? And then first pause and last pause both depend on nullable, okay? So if you want to calculate these three functions for all the nodes in this tree, it's best to calculate the nullable first, and then the first pause, and then the last pause, okay? Let's apply the nullable, okay? So, in all of these functions, we are going to calculate the values bottom up, okay? That is, we start the nullable for the leaf nodes, then we calculate the nullable for the parent node, then for its parent, and so on. We work our way up to the root of the tree, very much like some of the evals we did in the Lisp program, right? Okay, so interestingly, we don't have a leaf node which is the epsilon, so that's good or bad or whatever it is. So we don't have this situation, this true situation. Okay, so every other leaf node is false, nullable, right? So I'm going to put that. Let's see, where should I put it? Maybe on the top I'll put it. So this is false. Okay, nullable. This is false. Okay, I'm putting F just above the node for all the leaves. False, false, and false. Okay, so the F on top of the leaf, you'll put true or false. Okay, if the leaf is a regular symbol, you put false, and if it's the epsilon, we don't have an example of that, but if there was, then you'll put a true there. Okay, now all we do is apply these three definitions in the plus, the times, a product, and then the star. Okay, so the plus nullable is translates into an OR. So the nullable for this plus node here, there's only one plus node here, okay, which is way in the bottom there, okay. It'll be the OR of these two false, okay, false, whatever, I mean these two Boolean values, so we get a false here, okay, for the plus node. And actually that's the only plus node, so we won't be using this rule again. The next node we see is the star node, okay. And the rule for nullable for star node is always true, okay. So it doesn't matter what the value of the plus is, true or false, this will automatically become true, okay. The nullable for star node will be true automatically, okay. And then for the dot node, it's an AND of the nullables of the children. So this dot node, the one above the true false here, it'll be the AND of true and false. So true and false would be false, right? And then we have false and false will be false for that. And then false and false will be false. And false will be false. Okay? So we have calculated the nullable for all the nodes. Okay? There were so many dot nodes, and that's why we had to do the ANDs. True and false, false and false, false and false, false and false. So this is how you calculate the nullable. Very simple idea, okay? And actually, if you have to write the code for this, it's just going to be a recursive definition like you did the evals and so on, okay? Yeah. Okay. We're done with the nullable. Oh, that was easy, okay? Now let's do the first pause, okay? Now the first pause, I'm going to write to the left of this, to the left of the F, okay? Of the nullable, and then the last pause I'll write it to the right of it, okay. So that's where I'm going to write it, okay. So the first pause will be to the left of the F, and follow pause will be to the right of F, okay, if there is room. If not, I'll go past the bar, okay. So that's what we're going to do. We're going to write the first pause and the last pause now. Let's do one at a time. First pause, okay. So the first pause for the leaf nodes, if it is a epsilon node, then it will be the empty set, but we don't have an epsilon node. But otherwise, we will just write the position, okay, because that's what it says here, okay. The first pos is the set containing I, okay. So the first pos for the A node, the leaf node, would be 1, okay. You had to put it in the set, okay. And oops, I don't have a yeah, I guess I can put 1 to the left of this, okay. I guess I can put it to the left of this, yeah. So 1 for that, okay. Oh no, this will be 2, excuse me, okay, that will be 2, okay. The first pos for this A node will be 3. The first pos for the next one will be 4. For the B node up there it will be 5, and for the 6 it will be 6, okay. So the leaf nodes, the first pos is very simple. All you do is include that position of the leaf node into the first pos, okay. It will be a single item, okay. Now we generate the first pos at the interior nodes, and that would be, if it's a plus, then it will be union, and if it's a dot, then it will be the for the dot we had to check whether it's nullable or not. If the left child is nullable, then it's the union of the two children's first pos. Otherwise, it's just if it's not nullable, then it's the first pos of the left child, okay. Now here, just remember that there's only one node which is nullable, okay, which is this guy here, okay. So that node which I'm pointing to, that's the one which is nullable. Everything else is not nullable. So that observation might help us when we are calculating the value of first pos, okay. So you have to calculate the first pos for the interior nodes. So let's do the plus node, okay. The first pos there, because that node, its left child is not nullable, okay. Then the first pos there would be the first pos of the union of the two first poses in the children, okay. So it's going to be 1, 2, 1, 2 here, okay. Why? Because the left child is not nullable, okay. Therefore, we had to union the first pos of the left child and the first pos of the right child, okay, and which happens to be 1 and 2, and that's why we get the 1 and 2, okay. For the star, it's the first pos of, if you can look at the definition, for the star node, it's just the first pos of the child. So the star node's first pos will also be 1 and 2, the same as the value of its child, okay. Then we go to the dot above. So we are actually calculating the first pos for all the interior nodes now, okay. So now it's for this F node we're going to calculate the first pos, okay. And if the left child is nullable, then the first pos of that will be the union of the first pos of the two children. And actually, in our case, it is nullable. The left child is nullable, right? You can see that. So the first pos of the this node F here will get the 1, 2, and 3. 1, 2, and 3. Okay, all 3. Okay, 1, 2 from the left side and 3 from the other side. Mainly because the left child was nullable. Okay, if it's not nullable, then only 1, 2 will go up. Okay, but because it was nullable, we would have to include both the first pos of the left child and the first pos of the right child in the first pos of this dot. Okay. Now, the subsequent dot nodes above, all their left childs are not nullable. Okay. So we will just use the first pos of the left child as the value there. So this 1, 2, 3 will get carried over here to the first pos of this. Okay. Also to this 1, 2, 3, and also to the top 1, 2, 3. Okay. So the first pos of the top 3 dot nodes will be the same as the first pos of the fourth dot node, which is way down there. Okay. The dot node, because the left childs were all not nullable. That's why we have to just use the left child's value. Okay. If the left child is nullable, then you have to use the left child's first pos and the right child's first pos and carry over. And that's what happened here in this node. Okay. We had to use 1, 2 and the 3 and combine them together here. Okay. Got it. Okay. The dot node works like that. It's got an if then else. Okay. So we got the first pos for everything. Okay. Well and good. So let's do the last pos now. Okay. Last pass for the leaves is very similar to the first pass of the leaves. Okay, so and I'll write it to the right side. Okay, so I'll write it here: 1 to the right side, 2 to the right side. Just do the leaves first. 2 to the right side, 4 to the right side, 5 to the right side, and 6 to the right side. Okay, so I have placed the follow pass, not follow pass, what is it called? Last pass. Okay, I placed the last pass next to the index or the integer for the leaf node. Okay, so those are the last pass for the leaf nodes. Okay, and then we have to apply the last pass for the plus and the star and the interior nodes for those three operators. Okay, for the plus, it's the same as the union of the two sides. So if you look at the plus here, it will be the union of the last pass of the left side and the last pass of the right side, and that will be the same as the 1, 2. Okay, 1 from the left side and 2 from the right side. So that will be the last pass of the plus. Okay, and for the star, the last pass is the last pass of the child. So it's going to be the 1, 2 carried over here. Okay. Now the dots come in. Okay, only for the dot we have the if then else. If you notice in both the dots for the first pass and the last pass, we have the if then else. Okay, so we have to worry about whether the left child is now we have to worry about whether the right child is nullable. Okay, got it? Right child, because this is the last pass, so we have to worry about the right child here. Okay, now none of these interior nodes has a nullable right side. Okay, none of the 4 dots. Okay, so that's good news, because then we'll just copy the last pass of C2 as the value of the parent. Okay, got it? So the last pass of this interior node, this dot, the first dot, bottom dot, okay, would be the last. Oh, actually, this was a 3 here. I think so. I made a typo there. Okay, and that should be 3. So that 3 would be carried over here as the last pass of this. Okay. Because the right child is not nullable, that's why we just carry over the right child's last pass as the value of the parent. Okay, same thing here. The 4 will go up there as the last pass here, and the 5 will go up here as the last pass, and then the 6 will go up here as the last pass. Okay, so the last pass for all the interior nodes were just a copy of the right child's last pass. Mainly because the right child is not nullable. None of the right children are nullable. Only the left child of the dot node, the lowest dot node, is nullable, and that was used in the first pass. Okay. Lo and behold, we have the values for the first pass and last pass for every node. Okay, so drawing by hand may be a little bit tedious. If you have a bigger piece of paper and you write it carefully and follow the definitions carefully, you should be able to do this pretty quickly. Okay, but you can actually imagine writing Python code to do this is going to be very simple. Okay, it's going to be just a recursive, and actually the code is actually given to you in the definitions. Okay, here in this definition, this is exactly the code. I mean, you don't have a then keyword. You'll just replace that with a colon kind of thing. You see, so coding this part is quite straightforward, but doing it by hand, little tedious. But if you do understand the intuitions, I think you can go very fast on that. Okay. All right. So that's the 3 functions. The nullable. Let's go back to the slides. Okay. The nullable, first pass and last pass. That was step 3. Okay. Step 3 is to calculate those 3 functions for every node in the tree. Every node, the leaf nodes and the interior nodes. Okay. And the leaf nodes definitions are right at the top in these 2, and then the interior nodes can be one of these 3 kinds. So these 5 rows in this table gives you the complete definition for these 3 functions. Okay, and we can verify whether this picture on the slide is the same as the picture here, and it is. Okay, so I showed you how to work it out. First, draw the bare bones tree with the numbering 1, 2, 3, 4, 5, and then start writing the true false for the nullables and also the first pass and the last pass, and that's how you get some practice on this one. Okay, we're getting close. So 3 steps out of the 5 steps are done. 5-step process. Step 1 and step 2 I sort of combine together. Construct the expression tree and give numberings to the leaves. Okay, unique numberings to the leaves. Don't give a numbering to the epsilon node. Okay. And then step 3 is calculate these 3 functions: nullable, first pass, and last pass. Okay. Step 4 is interesting. It's called the follow pause. Okay, so I got the first pause, the last positions, first positions, and now the following positions. Okay, and actually the follow pause is the key part, which actually depends on the first pause. So in a sense, this is the hierarchy. Okay, the hierarchy is as follows: nullable is needed to define first pause and last pause. Okay, and first pause and last pause are needed to define follow pause. Okay, and that's what we're going to look at. What is the definition of follow pause and how to apply that? Okay, and then finally, out of the follow pause, you can do the DFA. Okay, so this is the order in which you calculate these intermediate functions. These three, in particular, nullable, first pass, last pass, and follow pass. There are 4 functions you have to calculate before you can actually construct the DFA. Okay, so those 3 of the 4 functions we just looked at: the nullable, first pass, and last pass. Now we are going to look at the follow pass. Okay, and here's the definition of follow pass. Okay, actually an algorithm is given. Okay. And the idea, again, the intuition is also, again, similar to the first pause and nullable and last pause. Okay, a follow pause of now the follow pause is not applied. A follow pause is not defined for nodes, but follow pause is defined for each of these positions. This 1, 2, 3, 4, 5, 6. Okay, so that's slightly different than the other. Okay, so when I start constructing the follow pause, okay, which I'm going to show here on the right side, okay, when I apply this definition, I'm going to compute it for each one of these positions: 1, 2, 3, 4, 5, 6. Okay, the follow pause is defined for these positions. Follow pause is not defined for these nodes. Okay, got it? Whereas the first pause, last pause, and nullable are defined for the nodes. Okay, and we have already done with that. Okay, so the follow pause definition is computed for the leaf nodes or the positions. Okay, in particular the positions of the leaf nodes. Okay, so follow pause of 1, follow pause of 2, follow pause of 3, follow pause of 4, follow pause of 5, and follow pause of 6. Those are the 6 sets we have to calculate based on this definition here, or actually it's an algorithm. Okay, and in general, the idea behind this is that for any position I, follow pause of I will contain the positions which can follow in a string for this following this particular position. Okay, so because that's really what we want to do in this whole DFA or in this language, is to identify which symbol can appear after which symbol. Okay, because once you know this symbol can appear after this symbol, then you have understood the meaning of the regular expression. Okay, so that's where the follow pause is very critical to construct the DFA. Okay, anyway, the idea is as follows, or the algorithm is as follows. Okay, it's the algorithm again. You would have to go. You have to work on this tree bottom up. Okay, you have to work on the leaves, and then the interior node, the parents, and then the parent, and the parent, and the parent, and the parent until the root. Okay, so this is a bottom-up calculation, exactly like we did for nullable and first pass and last pass. Okay, except that this time our starting point is going to be this follow pause array, or whatever you want to call this, dictionary. Maybe this looks like a dictionary to me. 1, 2, 3, 4, 5, 6 are the keys, and the values are the positions. Okay, so let's think of this as a dictionary where the key is so this is the key. Okay, and then the value would be here. Okay, we're going to place the value, which is the follow pause of I. Okay, so this is I. Oh, maybe the table should have been. This is I. Okay, I equals 1, I equals 2, like that. Okay, I equals 2, I equals 3, I equals 4. Oops, equals I equals 5. Okay, so that, and I equals 6. So there are the 6 I's because these are the 6 positions. And we want to compute the follow pause of I. So follow pause of 1, follow pause of 2, and so on. Okay, and the way these are calculated is you have to work the tree, and you have to focus only on the star and the dot nodes. You don't bother with the plus nodes. Okay, Got it? The interior nodes you look at, okay? For each node in the tree, if it's a star node or the dot node, then there's some work to do. But if it's a plus node, you skip it, okay? So that's what you can see the method. For each node n in the tree, if n is a concat node, then you do something. If n is a star node, then you do something, else pass, okay? If it's a leaf node, pass, okay? And if it is a plus node, pass it, okay? So pass means go back to the for loop, okay? So we had to work this algorithm bottom up, but only at the star nodes and the dot nodes, okay? And also bottom up. So we'll actually work on the star node first, this one, then this dot, then this dot, then this dot, and this dot. So there are 5 steps here, okay? And there is a different action for each of the dot and the stars, okay? Since we have a star here first, let's look at the star rule, okay? What this says is that, actually I can keep that here to the left of it and move this slightly here so we can actually read both of these, okay? Yeah, I think we can read both of these. So we are focused on the star node, okay? And the star node, it says that if it is n is a star node, then for each position in the last pos of n, okay, what is the last pos of star? I'll underline it, okay? It's this guy here, okay? The 1, 2, okay? So we have to focus on the last pos of the star node, okay? And for each I, so in this case, I equals 1 and I equals 2, for each of them, what we do is in the follow pos of I, which is follow pos of 1, we add the first pos of C2. Oh, excuse me, the first pos of N, okay? I was reading the other one, okay? So follow pos of I equals follow pos of I union follow pos of N. Now, in the beginning, we'll assume the follow pos of all of these is the empty set, okay? So you will have to initialize the dictionary to an empty set, all of them, okay? I'm doing that right now. You can actually see empty set, empty set, empty set, empty set, empty set, and empty set, okay? So that's the empty set. So you'll have to initialize the dictionary so that each of these has an empty set there, okay? And all we are doing is, if it's a star node, we take the first pos of the star node and add all those elements into the follow pos of I, okay? So in this case, we are going to look at the 1 and the 2. And we're going to take the first pos of the star, which will be the 1, 2 on the left side here. You can see that, okay? And those two would be copied here, 1, 2, union, you'll do that into this and this, okay? So the 1, 2 and 1, 2 will appear in the follow pos of 1 and 2, okay? So let me recap this. For a star node, okay, you take each item here on the follow pos, okay, not a follow pos, excuse me, last pos, okay, which is 1 and 2, okay? For each I in the last pos, add first pos of n, which is this particular node, okay? This star node is the n, okay? First pos of that, which is the value which is sitting here. Add those two values to the last follow pos of 1 and 2, okay? And that's exactly what we did here, 1 and 2, okay? So that's how you work a star node, okay? And we are done here, okay? So we are done with the star node now, okay? Now we go to the parent of that, which is the dot node, okay? And let's see what we do in the dot node, okay? If it's a dot node with the 2 children, so the C1 is the star node and C2 is the A, okay? For each item in the last pos of C1, okay, which is again the same 1, 2 here, okay? That's a lot. For each item in that, we need to add the first pos of C2, okay? And C2 is this A node here, and the first pos of that is 3. So what we do is we take all the items from here and add it to the I guess to the same follow pos 1 and 2, because it happens to be 1 and 2 here, okay? So this 1 and 2 is the last pos of C1, right, which is the left child of this. Interesting, it's the same 1, 2, into which we add the first pos of C2, which is the 3, okay? So when we process the dot node, the first dot node from the bottom, we'll add the 3 here and the 3 here, okay? So the follow pos of 1 and 2 initially got 1 and 2, 1, 2 from the star node, but they got the 3 from the dot node, okay? And then we are done with this dot node, so we go to the next dot node, okay? Now this dot node is very similar to the one below, right? So what we do here in the follow pos of 3, which is on the left side, okay, for each node in the last pos of the left child, which is 3 here, okay, we have to add the first pos of the right child, which is 4 here, okay, which is this one here, first pos of that, okay. So 4 has to be added into the first pos of follow pos of 3, okay. So the follow pos of 3 would get 4, okay. So it is 4 here when we process this dot node, okay. So we are done. That's all there is. So we are done with these 2 dot nodes, okay. Now we get to the next dot node, which is the last top but one below the top one, okay. And again, it's got the left and right child. Left child is the C1, right child is the C2. So for each item in the last pos of C1, which is the 4, so into 4, so last follow pos, we will add the first pos of the right child, which is 5, okay. So that's how the 5 will show up here, okay, in the follow pos of 4, okay. And I think in the similar way for the topmost dot in the follow pos of 6, in the follow pos of 5, which is here in the follow pos of 5, the 6 will show up, which is the first pos of the right child, okay. So the 6 will show up here when we process the topmost one, okay. And we have processed all the interior nodes, and we are done, okay. The follow pos of the hash will always be empty, by the way, okay. It can never get anything, so that will always be empty. So this can remain empty, the last one there, okay. Little tedious if you have to follow it by hand, but if you have to code it, it's very simple in Python, okay. But I want you to practice following by hand, okay. So you need to come up with your own in your head exactly how these things have been calculated, but the definitions are given there, okay. All right, so I think step 4 is done, okay. We got the follow poses here, okay, and also in the slides the follow poses are listed here, okay. That's it, and now we have reached the last step, okay. The last step is to generate the DFA, okay. And for this, what I will do is I will go up on the slides and make some empty room here, or not on the slide, on my iPad, okay. That's fine. And then we're going to look at this algorithm here, the generate DFA algorithm, okay. All right. This one uses only the follow pos. Remember this picture I had drawn? So in some sense, you can forget about the here. Let me get back to this picture. Yeah, here. So if you remember, this is the picture. Let me circle it. Okay, that looks like a nice egg or a potato. Okay, that looks like a nice potato. Okay, nullable is the first function you calculate, and once you calculate, you use it to calculate first pos and last pos. And once you calculate first pos and last pos, you use first pos and last pos to calculate follow pos, which means you can forget about nullable when you're calculating follow pos, okay. And similarly, when you're ready to construct the DFA, all you need is the follow pos. You don't need the first pos and last pos and nullables, okay. So in a sense, this is good news, because as you progress into the subsequent steps, if you got the previous functions correct, then you can 2 steps before the functions you calculated, you can forget about them, okay. All right, so now technically to construct the DFA, all we need is the follow poses, okay. And I think maybe I can keep the follow pos here, okay. I'm going to keep the follow pos here, and I'm trying to see whether I can construct the DFA down here, okay. Down here. Maybe I may have to bring this like this so I can have some extra room there, okay. All right, so the DFA construction works as follows. Start with the first pos of the root node as the start state in the DFA and designate it the start state, okay. So what you do is you go to the top of the tree. Oh, I guess you need the first pos, okay, of the root, okay. First pos of the root is 1, 2, 3, okay. Can you see this? 1, 2, 3 is the first pos of the root, okay. So you do need that, okay. So that part is needed. So I'm going to keep it like this, and our start state is going to be labeled with the value of the first pos of the root, which was 1, 2, 3, okay. Now I will ignore the braces. I'll just put 1, 2, 3 here. Okay, it's awkward to put. Oh, yeah, you can see that, right? 1, 2, 3. Yeah, here. I think I can move this to the left a little bit more. Okay, so this is my DFA construction. Okay, this is step 5. Okay, the final step. Okay, you take the first pass of the root, which happened to be 1, 2, 3. Okay, and first pass. Okay, and then use those numbers in that as the name of the state. Okay, 1, 2, 3. Okay, and that's the start state. Okay, and that's what the algorithm. And what you do is, and then you start collecting the states. Now, if you're writing a code, you might need a set, but because I'm drawing a picture, all my states are going to be shown by these circles here, so I don't need to maintain that set when I'm showing you this. Okay, but if you're programming this, you will probably put this into a set. Okay, this name into the set. Okay, okay. And what we do is we start off expand this state on A and B. Okay, so you can actually see that the final DFA is going to look something like this. Okay, down there. Okay, but we're going to follow this algorithm step by step, and I'm going to draw this here. So there are going to be transitions on A, little a and little b from 1 to 3. Correct. So we need to determine which state we need to go to on A and which state we need to go on B. Okay, we have to expand the transitions from this start state. Okay, and that's what this algorithm allows you to do. It tells you how to define the transitions for each state you create. Okay, so right now we created a start state, so now we have to define the transitions. Okay, and that's what it says here. Okay, so the while loop is basically to keep doing this, so we don't have to worry about the while loop when we are doing this by hand. So start setting up the transitions on this diagram, and once you've completed the diagram with no more transitions, then you're done. Okay, so that's what this while loop is. Okay, basically it's, in the programming you might have to mark it, put a mark, and then unmark it, and then mark it as soon as you enter the while loop. Okay, so this is just for the programming sake, but okay. Now what do we do? Okay, now what we do is I've explained it here. Here's the initial states. Okay, and what we do is this for loop I had to do. Okay, and in particular what we do is because we have two transitions A and B, we have to separate these state numbers, position numbers 1 to 3 into two groups. Okay, into the groups which correspond to little a and another group for little b. Okay, now you must remember that these positions are positions for the letters A's and B's, right? So if you want, we can actually go back to this picture and sort of write the positions here in this box. Okay, for A, if you look at it, A has got position 1 and position 3. That's all, right? A appears in positions 1 and 3. Okay, and B appears in positions 2, 4, and 5. Okay, might as well put the hash as position, which is 6. Okay, so that's how these are the positions. 1 and 3 are the positions for A. 2, 4, 5 are the positions for B, and 6 is the position for hash. Now that information is needed. Okay, when we are doing this. Okay. Okay, what we do is, maybe it's something like that. Okay, so we can actually see. So we got these positions. So inside the, when we are trying to expand this, we have to look at 1 to 3 and put them into two groups. One for A and one for B. We don't do the grouping for hash because none of these will be hash and it will come only at the end. Okay, so here you'll see that 1 and 3 correspond to B, correct? Oh, excuse me, 1 and 3 correspond to A, and 2 corresponds to B. Okay, and that's what this for loop says. Okay, the for loop says that for each symbol A, I mean A and B, I guess. Okay, one is A and the other is B. Okay, for each symbol in the alphabet. Okay, what you do is you must take the union of the follow pause of all the positions which correspond to that symbol. Okay, so in this case, if you want to do the A transition, okay, if you want to do the A transition, then you must go to a new state which is determined by the 1 and the 3 here are the A's, right? 1 and the 3 are the A's. Okay, I've sort of put arrows below them. Okay, so you have to go to follow pos of A1 and follow pos of 3, which is there in this table on the right side here. This is the follow pos of 1, 1 to 3, and the follow pos of 3 is 4. And you have to take the union of those two, combine those two. So you get 1, 2, 3, 4, and that's where you'd go here, 1, 2, 3, 4. Okay, so that's how you determine the transition on A. Now on a B, because this 2 corresponds to the B, okay, after 1, 2, 3, 2 corresponds to a B, so you would have to take the follow pos of 2, and there's only one of that, so which is 1, 2, 3, and that's where the B transitions will go to. Okay, so the B transition will actually loop back into this, because the B transition based on this for loop inside the generate DFA is there's only one position 2 for the B transition. So you go to the follow pos of 2, which is 1, 2, 3 here. Okay, and that's it. So that's the next state on B. So 1, 2, 3 on a transition on a B takes you back to B. Okay, so that's how you get this B transition there. Okay, and that's all. And then you keep repeating this process. Okay, so let's do this on 1, 2, 3, 4 now. Okay, so on the 1, 2, 3, 4, 1 and 3 correspond to A, right? So the A transition on 1, 2, 3, 4 will be the union of the follow pos of 1 and 3, which is 1, 2, 3, 4, right? So you can, which is exactly what we did. So the A transition here will come back to itself. Okay, again applying this definition. So you have to go to the follow pos of 1 and follow pos of 3 and combine them, which is 1, 2, 3, 4. And because this state is 1, 2, 3, 4, you'll put the loop back into this. Okay. Now on a B, let's see what happens. Okay, which will be the positions 2 and 4, right? 2 and 4 are the positions. So you'll go to follow pos of 2 and follow pos of 4, and you see that there is 1, 2, 3, and 5. Okay, so on a B, you'll transition to 1, 2, 3, 5. All right. So now we are done with the 1, 2, 3, 4 state, because we have determined where to transition on A, and we also determined where to transition on a B. Okay. Now we repeat the same thing on 1, 2, 3, 5. Again, divide this into groups of A's and B's. So the 1 and the 3 will be the A's. The 2 and the 5 will be the B's. You can look it up in this table here, small table. 2 and 5 will be the B's. So 1 and 3, again, the follow pos of 1 and follow pos of 3. When you take the union, it will be 1, 2, 3, 4. And that is, take you back on an A. And 1, 2, 3, 5, 2 and 5 correspond to the B's. Okay, I can put arrows from the top if you want. Okay, the 2 and 5, and the follow pos of 2 and 5 will give you 1, 2, 3, 6. Okay, so this on a B will take you to 1, 2, 3, 6. Okay, and continue. Okay, same thing on the 1, 2, 3, 6. Okay, so 1, 2, 3, 6, again the 1 and the 3 correspond to the A, right? 2 corresponds to the B, but 6 corresponds to the hash. We will come to that in a minute. But 1 and 3 correspond to the A. Union of follow pos of 1 and 3 is 1, 2, 3, 4. So on an A, you would come back into this 1, 2, 3, 4. And on a B, which is only the 2, we'll go to 1, 2, 3. Okay. So on a B, you would actually make a long transition back to the beginning B like that. Okay. Now the hash 6, there's nothing much to do there, so technically you can just ignore that. Okay, but if you do want to follow this, 6 is the hash, and hash follow pos is empty. Okay, so technically there's nothing there. So, and also there's no transition on a hash, so you can actually ignore this one. Okay, if you get the 6 in any other states, you can ignore that. Okay, and that's it. So this is the final DFA. Okay, the only thing left is to designate the final state. And the final state is designated by any state which contains the position of the hash symbol. And in this case, it will be the last one. So you'll put a double circle on the last one. Okay? The other 3 states do not contain 6, so they are not the final state. Okay? That's it. So here we have a DFA. Okay? This is the final answer, by the way. This is the end of step 5. Okay? It's explained here. I hope this picture matches the one which we have here. Let's see, I've sort of gone through individual I explained here I put it there, and iteration 2, iteration 3 of the while loop, and so on, iteration 4 of the while loop. So all the 4 steps. Okay, I've not shown the marking of the states because any state which doesn't have a transition is unmarked, and any state which has the 2 transitions is marked. Okay, and then the final diagram you get here, which I think matches BA, yep, then AB, yep, and then a B, A back, yeah, that's good, and then the last one was maybe I should do it this way. The last one was A going back to 1, 2, 3, 4, I think so, and the B going all the way back to 1, 2, 3. Yeah. So I think the diagrams match. So that will be the final DFA. Okay. All right. I think a little bit complicated, but focus on each step, one step at a time. Okay. So the first 2 steps are pretty straightforward. Use the grammar, or sometimes you don't even need the grammar because you know the 3 operators. So it's quite easy to construct the tree by hand. Okay. And then assign the position numbers in the bottom in the leaves, and then step 3 is the nullable first pass and follow pass, which are these values here, these 3 things here for every node. The first pass is here, the follow pass is there, and the nullable is up there, and go in this order: nullable first, then first pass, last pass, and the follow pass, which is start with a dictionary and put empty sets for all of them, and then start processing the star and the dot nodes from bottom up. Okay, and then use the definition to fill these up. And once you have the follow pass, the final DFA construction is, I think, relatively straightforward. All you have to do is, given a state with the position numbers, you have to separate these into 2 groups, one for A and one for B. Okay, and then all you do is take the group for A and take the follow passes for each of those items in that, and then union them, put them together. Okay, and that's how you get these 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6, and so on. Okay. And keep expanding this until all the transitions are defined. Okay. Now this will not go on forever. Okay, because there's only finite number of states, finite number of positions. So in this case, we got lucky with only 4 states. But sometimes you might get 6, 7, 8 states, and so on. But it won't go on forever. It's going to stop at some point in time. Okay. All right. I think this is a good place to stop. It's also 42 minutes. That completes this topic. It's an interesting algorithm. I think we're going to get some practice both in the homework and actually also this is my project 1, by the way. So when we are going to do project 1 in the middle of the semester, hopefully in another week or 2, I'll assign the project. So we are actually going to code this algorithm using the PLY system and the Python. Okay, and we're going to see how it works. Okay, so that's coming up in the next few weeks. Okay, the first of the 2 projects which we have in the class. Okay. All right, I'm going to stop the recording here, and hopefully you have understood. If not, watch it again, watch the video again. If not, I can try to give explanations in the class if I see you. Okay. All right.